So the bottom line, the point here is that in this ratio, there is no sampling variance, and you can measure this quantity here, the bias, without the sampling variance. You can then feed that information into the three-dimensional information of the galaxy clustering, and therefore you can use lensing and the full three-dimensional information to reduce the errors. So you can get basically the best of both worlds. Okay, I was skeptical about that because, and the reason for that is there's actually a lot of stochasticity in this ratio. Galaxies are a stochastic tracer of dark matter. So not only we don't know the bias, but there's actually a lot of scatter in that relation. In fact, it's even worse than what theories predict. Theories usually predict it's Poisson noise, and this is what Poisson model would have predicted, but actually what we measure. This is what Poisson model would have predicted for uniform weighting of galaxies, but this is what we measure. However, what we have found recently is that if you weight galaxies by halo mass, then you kind of mimic the dark matter, and in relation to dark matter, you dramatically reduce the stochasticity. From this is what is predicted to this. Picture is worth more than this kind of plots. Let me just show you this. This is what we had before. The blue is the scatter plot between the mass and the density if you use uniform weighting. You see there's a lot of scatter here if you just use normal type of analysis that we have done before. A lot of scatter, a lot of stochasticity. Right? If you do this mass weighting that I'm advocating, then we get this relation here. The scatter has essentially completely gone away. It's incredibly tight. So in other words, you just pick one point anywhere in this relation, and you will know the relation, this bias relation between the galaxies and dark matter, if you use this mass weighting. Okay, so that's something that is worth pursuing in the future. So let me now, in summary, just say the comparison between shear and halo shear. Shear analysis, we all know. The lesson from last decade is that shear analysis is difficult. Okay, why is this so? Well, there's several. Let me go through this. Issues. Calibration bias is what I call is basically a relation between how you go from lithricity to shear. They both suffer equally from this problem. So I don't think halo shear is any better than shear. So this is actually one of the major issues that we have to deal with, how to do this calibration. But we have these, simulations, the step comparison and stuff like that, we think we can do a good job on this. Intrinsic alignments. As we know, intrinsic alignments are a problem because galaxies in front and galaxies in the back could be correlated. One is intrinsically aligned in the tidal field, due to the tidal field. The second one is sheared by the same tidal field. And there's a correlation, and that leads to intrinsic alignment that cannot be removed by having the galaxies physically separated. Right? On the other hand, if you do galaxy lensing, there is no problem like that, in principle, if they are separated. Okay? So there's some advantage on that here. Again, this goes back to the fact that we know the redshifts, and the signal is localized. Photometrically induced errors, I think, are a big problem. It's not clear if the problem is larger or worse for these two methods. So I just put a minus in both of them. One has to work hard on both. Instrument and sky-induced correlations. This is where I think that there's a big advantage in doing this technique than this technique. Of course, we know that, especially in Sloan, we don't even bother to try this to do the shear analysis. We know there's no hope we can do this because there are so many systematics that we would have to solve. But as a lot of you in this room know, the similar problems appear also in CFHDLS and also in the future design experiments. This is the hardest one to deal with, right? And how do you remove, systematically induced shear correlations, right? That's by far the hardest one. In contrast, if you do just analysis around a given object, most of these systematics disappear. For example, I don't know, you can do the same analysis around a random object and just subtract and stuff like that. So this is a big advantage of the shear halo analysis. Baryonic effects, again, actually, you would think that this is actually less sensitive to baryonic effects, but in fact it's not true, because if you do shear analysis, you're basically projecting signal from 0 to a given distance. So you always include small scale information, the stuff that is close to us. It's not that easy to remove baryonic information because it projects to any angular scale. On the other hand, if you do this, then you can just safely eliminate small scale information. In fact, I've shown you the techniques how we can completely eliminate small scale information. Small scale information means the one that is contaminated by issues of astrophysics like gas cooling and stars and adiabatic contraction and stuff like that, stuff that we don't think we have under control, at least at required accuracy. So there's an advantage, I think, for shear halo. Statistical power is another place where I think these techniques have an advantage. First of all, as I said, we don't work with angles, we work with physical separations. And then if you do this combination of 3D clustering with the 2D cross correlation to eliminate to get the best of both worlds, as I mentioned, then in particular you certainly gain a lot on the statistical power with these methods compared to these methods. Okay, of course, well, I guess I should have mentioned that the 1 minus is the theoretical relation. 1 minus for this method is the theoretical one. Well, how are halos and dark matter related to each other? But as I was trying to convince you in the first part of the talk, I think we have made a lot of progress on that, and we think that the relation is actually much simpler than what was previously taught, and we think that at least at the level of 1%, we already know it today, and then to go to 0.1%, we'll have to, I guess, work harder in the future, but there's hope that we can do this. All right, so this is the summary, and I'm not going to read through this, but I just want to, read the last point, which I hope is a topic for discussion for tomorrow, which is, it's possible that the shear will become just a consistency test, and most of the statistical power could come from these cross correlation techniques with the galaxies. Right? I want to be intentionally provocative a little bit here, just so that we have some fruitful discussion about this tomorrow, right? And perhaps the plan B, which is this, I always hear like Pan-STARRS people telling me, we always have a plan B. We'll do galaxy lensing if shear doesn't work out, right? But maybe plan B should really be plan A. Let me stop here.
Questions for Uros? Yes.
On your Tevis constraint, I was wondering, Tevis contains a free function that essentially tells you how to interpolate between large scales, the cosmological scales and the small scales. How sensitive is your constraint to this function, to this degree of freedom that you
No, right. We have assumed we are in large scale, so we have used the linear predictions. So because we think in this case we are, we are large scales, 10 megaparsecs and above. So otherwise, the predictions I've seen are kind of oscillatory and stuff like that, and then below 10 few megaparsecs, I guess nobody knows. I should say, Tevis, there's only been one model that has been worked out by Dollars and company, and that's what we used. I'm not claiming we rule out the whole family of Tevis models. On the other hand, it is generic for Tevis models. They have to introduce vectors. Vectors generically do enhance the growth of structure on small scale, so they do make the logarithmic growth rate larger. And so I think this is a generic prediction, but then whether this is true for all the Tevis parameters, that we don't know.
Okay.
Same note, is it just a pure Tevis model, or is that a Tevis plus some minimum amount of dark matter?
No, this is just Tevis.
So if you throw in the dark matter that the clusters seem to require, that could be even worse.
Well, you mean clusters like a bullet cluster?
Even normal clusters now need about 50%.
Well, you see, this is the thing, right? I mean, these people claim, the Tevis proponents, which I'm not one of them, but they claim that, well, we haven't really worked it out Tevis on small scales. They create their own dark matter, but it's in the model. It's this V, right, and vector field, which actually acts like dark matter. And so they claim that they can explain, for example, bullet clusters and other stuff because they have this vector field. So in their arguments, these clusters are not decisive because they think they have their own dark matter basically, but it's a vector field, and they think they can explain these things. So, and it's actually very difficult to work out what the cluster predictions are. It's non-linear, and this theory is non-linear and stuff like that. So it's not so easy. So which is why doing the linear calculations, which have been done, is in a way easier because you can track. At least the predictions are reliable because they're linear. So that's maybe another argument why this is a different kind of test than the clusters. The cluster is a very non-linear test, and certainly the Tevis proponents they try to discuss it.